Hi, this is Gerardo, and this is a tutorial about diodes applications for the electronics class. This tutorial will be divided in 4 parts. The first part is transformers, second, half-wave rectifier, third part, full-wave rectifier, and fourth part, full-wave rectifier with a filter. These diode applications is to transform an alternate current to a direct current. We're going to see transformers. A transformer in this tutorial will be an ideal transformer. This ideal transformer has a key concept, which is the turns radius. This is the physics model where you have a coil with an X number of turns, and in the other side you have another coil with an X number of turns. So this is the formula that connects the voltage 1 with voltage 2. This is symbol for an electronic circuit analysis. So here we have our first example, where we have a voltage source, a resistor, and a transformer, and we want to get the current that is getting out. So we're going to use these formulas. First, we're going to get the current in. For this, we are going to use Ohm's law. Now that we have our current in, we are going to get our current out with our turns radius. So in this example, we can see that we are getting current in, and with the transformer, the current decreases. In this case, we're going to see a voltage source, a transformer, and a resistor. And we're going to get the voltage out, current out, and the current in. First, we're going to get voltage out. So what we get here is that our voltage out is 4 volts root mean square. Now we are going to get the current out. To get this, we are going to use Ohm's law. We did here that the current out is 0.8 amperes root mean square. Finally, we are going to get the current in. Okay, we already have our current out, our current in, that is 0.16 amperes root mean square. Now we are going to continue with the half-wave rectifier. Here we have a circuit with a voltage source, a diode, a silicon diode, and a resistor. What we are going to do is to analyze this circuit in the positive cycle and in the negative cycle. So, positive cycle, using KVL, it's going to be this. So here we have that in our positive cycle, we're going to have 11.3 volts RMS in our resistor. In the negative cycle, what is going to happen? Our diode won't let the current pass. In the positive cycle, we have the current going this way, but in our negative cycle, we have the current in this way. When it gets to the diode is going to open, and the behavior is like an open circuit. So there's no current, so there's no voltage. So the negative cycle, Vx is going to behave 0 volts. So when we graph this behavior, we have the positive cycle, then 0 volts, positive cycle, 0 volts, positive cycle. From here, this is an altered current, but we can get the equivalent of a direct current that is given by this formula. It's an integral from the altered current, and with all the procedure, we get to the voltage peak over pi times. So in this case, we will get our direct current will be about 5.08 volts. Now that we have made a half-wave rectifier, we're going to make a full-wave rectifier. Here we have this circuit. Above the source, a transformer, we are getting a V out, and with this V out, we have what is called a diode bridge. What is going to make this diode bridge? When it's in positive cycle, we are going to draw again the circuit. We are going to have this circuit. So the current is going to be moving in this way. In the other diodes, it will behave as an open circuit because it is going against the current. So the circuit we're going to have is going to be something like this. So it is easier to analyze. So here, the first step is to get V2. So you go again with the transformer. Here we have that our voltage out is 12.5 volts root mean squared. So we need the peak value of the voltage that is given by this formula. Well, so now that we have this value, we can make KVL for the positive cycle. This voltage source is going to be from 70.67 volts, silicon diode 0.7 volts, silicon diode 0.0 volts, and we're going to get the voltage of the resistor. KVL so we have a voltage peak of 16.27 and the voltage at the resistor, sorry. So now we're going to make an analysis of the negative cycle. So we have this here. So in the negative cycle, it will be we're going to have this circuit. We can see that KVL will result get the same result as we get here. We can see that the circuits are equivalent circuits where we have a voltage source, two diodes, and a resistor. The same value for the voltage source and the same value for the diodes, so we have the same value for the voltage at the resistor. Finally, we can graph our circuit with the voltage against time on the resistor. It's going to be a peak value, then again the peak value in the positive side. So we can get again our direct current, but this time because we have a half of the frequency that we used to have in the halfway rectifier, it's going to be 2 times the last formula. So it's going we are going to have 10.35 volts of direct current. To finish this tutorial, we are going to analyze a full wave rectifier with a filter. What is this filter? This filter is a capacitor that will behave in the analysis of the voltage against time as a direct current. We have our voltage source, our transformer, a diode bridge, resistor, and a capacitor. So the first step is to get V2. Now we have our voltage peak that is 14.1421 volts. Now we are going to make our positive cycle. We're going to make KVL. With KVL, we get that our voltage at the resistor is 12.74 volts, and because it is in parallel with the capacitor will have also 12.74 volts. This voltage in the capacitor, as you may remember of a circuit analysis course, the capacitor is going to discharge over the time. So when we have the negative cycle, our capacitor is going to be supplying a voltage. This is going to be our circuit in the negative cycle. But what we need here is the ripple. We can get the ripple with the following formula. This is the peak value of the voltage, the frequency of the alternate current, the resistor load, and the capacitor. So we can get this data from our circuit. It's going to be this value means that the difference between our peak voltage and our lowest voltage is going to be about 2.12 volts. So at the time we're going to graph, our graph will look like this. First, we have our peak voltage. In our positive cycle, it gets to 12.74. But when it's discharging, it won't discharge as an alternate current. It will discharge according to the capacitor. This means it will discharge something like this. So when it comes again, the positive cycle, it will charge again the capacitor and discharge. Charge and discharge, charge and discharge. So we are going to have a 12.74 volts as peak. And as the minimal value, we are going to have 10.6167. Now again we can get our voltage as direct current, that is the sum of these two values over 2. 12.74 plus 10.62 over 2, and the result is 11.68 volts. So now, with this tutorial, we can know how to make a diodes application. In this case, we transform from 100 volts root mean square to 11.68 volts. This can be taken to charge, for example, a cell phone, a computer, a calculator, but there are a lot of applications.